Okay, let's get started with the continuation of the Organic Chemistry 1 lecture series. Today we're going to be discussing Chapter 7, which focuses on alkenes and reactions of alkenes. First and foremost, let's provide a definition of alkenes and let's review this concept of degree of unsaturation. First and foremost, what is an alkene? An alkene is a hydrocarbon containing a carbon-carbon double bond. Alkenes can also be called olefins, but alkene is a more accurate and more commonly used descriptor. Why do we care about alkenes? Well, alkenes are very useful functional groups in that alkenes can be converted to other functional groups with stereoselectivity and regioselectivity. We can take a feedstock alkene such as ethylene and convert it through chemical reactions to a range of other functional groups such as alcohols, aldehydes, ketones, epoxides, alkyl halides. So alkenes are really useful functional group handles that can be converted to other functional groups. Now, one idea that's related to structures containing pi bonds or rings is this idea of degrees of unsaturation. So unsaturated compounds are compounds containing pi bonds or rings. The degree of unsaturation, or Du, indicates the number of multiple bonds or rings in a given formula. Du can be calculated using this expanded formula here, while if you have just a simple hydrocarbon, Du can be calculated by taking 2 times the number of carbons plus 2 minus the number of hydrogens divided by 2. Again, when we calculate Du, we're calculating the total number of pi bonds or rings in your given structure for a given formula. For example, if we had the formula C6H10, that gives a Du of 2 times 6 plus 2 minus 10 over 2, which gives us a Du value of 2, which tells us we have 2 pi bonds or rings. This can be accomplished, and if we wanted to draw a reasonable structure for this formula, one example would be 4-methyl-1,3-pentadiene, which has 1, 2 pi bonds, cyclohexene with a ring and a pi bond, this bicyclic structure with 2 rings, or even a structure containing a triple bond. So Du is really useful to calculate for a given formula because it allows you to very efficiently draw out constitutional isomers for that formula. Let's do some case studies now. If we are given the formula C4H6Br2, we can see from the structure for this formula, we have a Du value of 1. We have 1 pi bond or ring. If we wanted to calculate Du manually, halogens are treated identically to hydrogens. So in this case, we take 2 times the number of carbons plus 2 minus the number of halogens, where we have 2 bromine atoms, and then we subtract the number of hydrogens divided by 2. So this in turn gives us a Du value of 2 over 2, which matches our Du value of 1 that we calculated. Let's now try another case study. We have a formula C5H5Cl. Let's take a few moments. Let's calculate the Du for this formula. And then from here, let's try to draw a reasonable structure given this formula. So pause the video, work through that, and then we'll discuss. Okay, so for C5H5Cl, for our Du, we take 2 times the number of carbons plus 2 minus the number of hydrogens minus the number of halogens, which is 1, divided by 2. This in turn gives us 6 over 2, which is a Du value of 3. So we have a total of 3 pi bonds and or rings. So I'm going to draw a ring with 2 pi bonds, and this satisfies our Du value of 3. And as you see, we have 5 carbons, 5 hydrogens, and a chlorine atom in our structure. Let's do some more case studies, this time looking at C5H8O. Oxygen, as we see from our DU formula, counts neither towards nor against the DU value. We just sort of ignore oxygen in the DU calculation. Looking at this structure, we have 1, 2 pi bonds, so we'd expect a DU value of 2. Let's calculate that. So we have 2 times the number of carbons plus 2 minus the number of hydrogens divided by 2. This gives us a DU value of 12 minus 8 over 2, which gives us 4 over 2, which is a DU value of 2. Looking at this last example, this time involving nitrogen, here we have a pi bond and a ring, so we have a DU value of 2, but let's justify that with a calculation. Nitrogen is counted as plus the number of nitrogen atoms in the DU calculation, so let's account for that. So we have 2 times the number of carbons plus 2 minus the number of hydrogens plus the number of nitrogens. We have 1 nitrogen atom, so we add 1 to our total. Okay, this gives us a DU value in this case of 1, 2, 3, 4, 5, 6, 7, 8, 9. 2 times the number of carbons plus 2 minus the number of hydrogens plus the number of nitrogens divided by 2. Okay, so in this case, we have 13 minus 9 over 2, which gives us 4 over 2, which matches our structurally identified DU value of 2. Okay, perfect. So let's talk a little bit now about alkene stereochemistry, as it's very important to identify your starting alkene stereochemistry, as it has a huge impact on the product stereochemistry for alkene reactions. So alkenes can have geometric stereoisomers if there are 2 unique substituents on each alkene carbon. Cis alkenes or Z alkenes have the highest priority substituents on the same side. For example, here the chlorine substituents are our high priority substituents. They're on the same side. This is a Z alkene. Trans or E alkenes have the highest priority groups on opposite sides, as observed in the following E alkene. Given what we have learned about E and Z nomenclature, looking at the following molecule, we see that the fluorine and the oxygen atom, which are our highest priority substituents, are on the same side. So this would be a Z alkene. While in this other molecule, because the fluorine and oxygen atom, the high priority substituents are on opposite sides, this would be the E alkene. Now, in terms of assigning Z and E configurations for alkenes, in cases where there are multiple substituents, we're going to utilize the IUPAC convention for Z and E assignments. In this method, you rank each group on each side of the alkene separately in order of priority. Priority, remember, is based on atomic number. If the highest priority groups are on the same side, the alkene has a Z configuration. Well, if the highest priority groups are on opposite sides, the alkene has an E configuration. For example, E2-chloro-2-butene, it's E because the 2 high priority substituents are on opposite sides, while Z2-chloro-2-butene is Z because the high priority substituents are on the same side of the double bond. With that discussion in mind, let's take a few moments and let's assign the configuration for the following 2 alkenes. So pause the video, take a few moments to work on this example, and then we'll discuss. So first and foremost, let's start with this left example. Fluorine is higher priority than carbon. Additionally, this alkyne, remember an alkyne is really treated as if there are two additional carbon-carbon bonds connected to the alkyne carbon. So this, even though we have two carbons, this carbon is connected to 1, 2, 3 carbons and a hydrogen versus a carbon and two hydrogens. So this top group, well, technically a carbon, and two hydrogens. So this top alkyne is higher priority than the alkane. From here, as we can see, our highest priority substituents are on opposite sides, so this would be an E alkene. Looking at this next example, the ethyl group is higher priority than the methyl group, and the carbon attached to an oxygen is higher priority than a carbon attached to carbon. Because our highest priority substituents are on opposite sides, again, this would be another E alkene. Okay, so as we're talking about alkenes, it's important to talk about alkene nomenclature. So when naming alkenes, you're going to name the parent hydrocarbon chain by finding the longest carbon chain containing the double bond. So in this case, as we can see on the left, we find the longest carbon chain containing the full carbon-carbon double bond. So this has 1, 2, 3, 4, 5 carbons. So this would be a pentene carbon chain. By the same token, if we look at this molecule here, we're going to identify the longest chain that contains our double bond. So it would be this chain here. Now, when numbering your carbons, your carbon numbering will start from one side of the molecule, passing through the double bond and end at the other side of the molecule. For example, in this case, we'd number 1, 2, 3, 4, 5, numbering through the double bond. So as you can see, we have an ethyl group at the 2 position. So this would be 2 ethyl. And we note that the double bond starts at carbon 1. So this would be 2 ethyl, 1 pentene. Importantly, when you assign your locant numbers, you're going to count carbons to give the smallest possible locant number for the carbon-carbon double bond, and you'll use the smallest locant number to indicate the double bond location. For example, we number this molecule, counting through the double bond, giving the locant number 1 for the double bond if possible. 1, 2, 3, 4, 5. As you can see, we have a substituent at position 2. Looking at this ring, again, following our rules, we're going to assign the double bond the lowest locant number. So we have 2 possibilities, 1, 2, 3, 4, 5, or counting through the ring in the opposite direction, 1, 2, 3, 4, 5. Now, how do we break this kind of tie? Substituents must have the lowest possible locant numbers after assigning the lowest possible locant for the carbon-carbon double bond. So, in this case, we have the following locant numbers. As we can see in this initial example, when we numbered through, we numbered such that we gave the lowest locant number to this methyl substituent. This is compared to the alternative numbering method that's shown in blue. As you can see, if we have a choice between giving the substituent a locant number of 2 or 5, given that the double bond has the same locant number in both numbering methods, we're going to prefer the locant numbering method in red as it places the substituents with the smallest locant numbers overall, and it gives the double bond the smallest locant number. By the same token, as we discussed in this middle example, we numbered it 1, 2, 3, 4, 5, counting from right to left, versus 1, 2, 3, 4, 5, counting from left to right, for 2 reasons. First, we want to give the lowest locant number to the double bond, and that is our immediate concern. But also, we want to give the lowest locant number to our substituent. So that's why we choose the numbering method in black rather than in blue. Going back to the question of this cyclic system, given our two choices, let's take a look at these two choices that we discussed, and let's see what the difference is. So in either case, for our two numbering methods, we have a locant number of 1 for our double bond. Now, in our two choices, we can either assign the methyl groups locant numbers 3 and 5, 3 and 5, and 1 versus 2. So let's list our possible locant numbers here. In purple, we have locant numbers of 1 and 5. In blue, we have locant numbers of 2 and 3. Now, we want the lowest locant numbers in order, so the locant number of 1 wins out over the locant number of 2. So we're going to use the numbering method in purple, counting through the double bond. And as you can see, we give the double bond a locant number of 1, the methyl group a locant number of 1, and the other methyl group a locant number of 5. So the only thing that changes when you have an alkene is you have to count through the alkene. The alkene gets the lowest locant number, and then once you've satisfied that condition, then you try to give the substituents the lowest locant number. So once we have your locant numbers established, you're going to number and name the alkyl substituents following alkyl group nomenclature rules. Write the substituents in alphabetical order, specifying the carbon number for each substituent. You're going to replace the ane ending with the locant number followed by the ene suffix. For example, looking at this molecule here, we have a methyl group at the 2 position, so we name the substituent 2-methyl. Then we note the locant number of the alkene, which is 3-hexene. Notice we change the suffix to ene. Another older method would be to name this compound as 2-methyl 2-methyl hex 3-ene. Both of these naming conventions are commonly used, but I would prefer you use the naming convention where you place the alkene locant number before the full chain name. So, continuing, looking at this middle example, given that we have the following locant numbers. At carbon 2, we have an ethyl group, so we name this as 2-ethyl. The carbon-carbon double bond starts at position 1, so this would be 1. We have a 5-carbon chain, so it would be pentane, which we change to pentene. So this would be 2-ethyl, 1-pentene. Finally, looking at our last example, as we note, the methyl groups are at position 1 and 5. So we would name this as 1,5-dimethyl. And then we note the carbon-carbon double bond starts at 1. So this would be 1-cyclopentene. So this would be 1,5-dimethyl, 1-cyclopentene. Okay, so let's talk now about what happens when we try to name alkenes when there are multiple alkenes and when the alkenes have stereochemistry. So if there are multiple alkenes, you'll use diene, triene, etc., and you'll specify the location of each double bond. For example, this diene would be named as 2-methyl 1,3-butadiene, noticing that the first double bond starts at carbon 1, the second double bond starts at carbon 3. So if we're naming, so here's another way to look at it. Here's the bond line depiction. As you can see, we have the methyl group at carbon 2. The double bond starts at carbons 1 and 3. This would be 2-methyl 1,3-butadiene. Let's look at another example. In this case, we have another diene. We're going to count such that our longest chain contains both of the alkenes. As we can see, the carbon-carbon double bonds start at positions 1 and 4, and we have an ethyl group at carbon 3. So this would be named as 3-ethyl 1,4. Because this is a 5-carbon chain, this would be pentadiene. Now, when we have these cyclic systems, you're always going to want to make sure to count through both carbon-carbon double bonds. And so in this case, we have carbon-carbon double bonds at positions 1 and 4. So this would be 1,4 cyclohexadiene. Cyclo, because it's cyclic, hex, because it's 6 carbons. Now, where things get interesting is what happens when you have an alkene with some stereochemistry. In this case, the configuration of the alkene is indicated at the beginning of the name, italicized and surrounded by parentheses. For example, in this case, because we have an E alkene and the alkene is at carbon 2, this would be 2E but-2ene. You can also call this 2E 2-butene. The old school and newer methods of naming this compound. Key thing, you need to have the locant number and configuration for the alkene if it has stereochemistry. Let's look at this next case. So let's draw out our hydrogens. This is a textbook Z alkene. Numbering, we want to number through the alkene to give the alkene the lowest locant number. As you can see, we have a methyl group at carbon 4. Why do we choose this numbering method? Because if we number in the opposite direction, the alkene would get a higher locant number, and the alkene gets priority. So in this case, we have a Z alkene starting at carbon 2. So this would be 2Z, 4-methyl, 2-pentene. 2 because the alkene's at carbon 2, and pentene because we have a 5-carbon chain. Now, if a molecule contains multiple double bonds, the locant and carbon number of each chiral center is noted and indicated before the configuration. So for example, in this case, we have 2 E alkenes at positions 1, 2, and 4. So we have the alkene starting at positions 2 and 4. At position 2, this is an E alkene. At position 4, it's an E alkene. So this would be 2E, 4E, hexa, 2,4-diene. Why hex? Because it's a 6-carbon chain. Let's try to apply what we've learned, and I'd like you to take a moment and try to name the following compound. I will give you a hint that because we want to give the alkenes the lowest locant number, you would number it as follows. Okay, so pause the video, work through that, and then we'll discuss. So first and foremost, the two substituents that are high priority are on the opposite side of the double bond. So this first alkene is E. The second alkene, the highest priority groups are on the same side. So this will be a Z alkene. From here, we note that we have a methyl group at position 4. So we name this as 2E, 4Z, 4-methyl, and then 7 is hept, so it would be hepta 2,4-diene. Perfect. So we discussed all the naming conventions for alkenes. Let's talk a little bit now about the stability of cis and trans alkenes and the effects of substitution on alkene stability. So if we look at the relative stability of cis and trans alkenes, cis alkenes are less stable than trans alkenes due to steric strain. This is evidenced by the fact that trans-butene has a lower heat of hydrogenation, implying the trans alkene is lower in energy. In many cases, if you have an equilibrating reaction where the cis and trans alkene can interconvert under equilibrating conditions, the lower energy, more stable trans alkene is favored. Now, in terms of substitution, alkenes are stabilized by increasing substitution, with a tetrasubstituted alkene being more stable than a trisubstituted, which is more stable than a disubstituted alkene, which is more stable than a monosubstituted alkene. Now, why is that? Alkenes are stabilized by hyperconjugation. Electrons in neighboring filled sigma bonding molecular orbitals can stabilize the vacant pi star orbital. So if we have a double bond, which is a pi bond, that pi bond's pi star orbital can interact with an adjacent sigma bond, and that stabilizes the pi star orbital. In essence, the more groups you have on your alkene, the more substituted your alkene is, the more stable your alkene will be. If we wanted to draw a monosubstituted alkene, these would both be hydrogens. Monosubstituted, one substituent. Disubstituted, two substituents. Trisubstituted, three substituents. Tetrasubstituted, four substituents. The more substituents you have on the alkene, the more stable your alkene will be. Why? The alkene stabilized via hyperconjugation with adjacent sigma bonds. We've talked a lot about alkenes. Now let's talk about some modes of alkene reactivity. One of the more common ways that alkenes can react is via electrophilic addition. In electrophilic addition, a nucleophilic pi bond is used to form two new sigma bonds. In the most common type of electrophilic addition, which is hydrohalogenation, the alkene is protonated by forming a carbon-hydrogen bond, then the carbocation is attacked by the nucleophile. So in the first step, we protonate the alkene, and then the carbocation gets attacked by the nucleophilic halide ion. Because carbocations are so reactive, your nucleophile can be quite weak. To practice this, we have another substrate here, and let's practice drawing the mechanism. One thing I would like you to note is that for electrophilic addition, as we discussed in prior chapters, the protonation is going to occur to make the most substituted, most stable, lowest energy carbocation. So if we protonate this alkene, we're going to protonate to make the tertiary carbocation. And from here, your nucleophile, which is going to be the bromide anion, is going to attack and form the desired carbon-bromine bond. When we run electrophilic addition reactions, we run them at low temperatures to avoid elimination. As a refresher, let's now talk about the electrophilic addition energy diagram. In electrophilic addition, alkene protonation to generate the carbocation is the rate-limiting step. The kinetic pathway favors generating the lowest energy, most stable carbocation. In other words, the reaction that produces the more stable carbocation occurs at a faster rate, and thus, as we've seen, if we have a choice between a primary and a tertiary carbocation, reaction will favor generating the tertiary carbocation product. Let's talk about the regioselectivity of electrophilic addition, and let's talk about a rule known as Markovnikov's rule. As we've seen, for most alkenes, there are two possible addition products. Electrophilic addition of HX reagents such as hydrochloric, hydrobromic, and hydroiodic acid is regioselective and follows what's known as Markovnikov's rule. In Markovnikov's rule, the halogen is generally installed at the more substituted carbon, while the hydrogen is generally installed at the least substituted carbon. So for example, if you have a choice between a primary and tertiary position, the halide is installed at the more substituted tertiary position. Now, you can run into some issues with certain substrates where if both ends of the alkene have similar substitution, then the addition is not regiospecific. For example, if you have a choice between two secondary positions, you'll get a mixture of hydrobromination products. Now, there's a rephrasing or restatement of Markovnikov's rule that'll be a more general way of predicting the products and predicting the outcome of electrophilic addition reactions, which is the more stable carbocation forms as an intermediate rather than the less stable carbocation intermediate. And generally, this means you'll get the most substituted carbocation intermediate. So for example, when 2-methylpropene reacts, it will prefer to react in the initial protonation step to make the more stable substituted tertiary carbocation rather than a primary carbocation. Why? The tertiary carbocation is more stable and it's easier to form. So let's try to apply what we've learned in terms of Markovnikov's rule. So let's try to predict the major product from the following reaction. So we have an alkene reacting with hydrobromic acid. You don't need to draw the mechanism, but you can if you want. I just want you to tell me what the major product is from this reaction. So pause the video, work through this example, and then we'll discuss. So first and foremost, we have our initial protonation step. We have a choice between a secondary and a tertiary position. The tertiary position is more substituted. So we will protonate to generate the more stable, more substituted tertiary carbocation. And that tertiary carbocation is immediately going to get attacked by our halide nucleophile, and that in turn generates the Markovnikov regiochemistry product, where the halogen is installed at the more substituted tertiary position. Wonderful. Let's talk a little bit about the regioselectivity of electrophilic addition from the perspective of carbocation stability. Resonance stabilized carbocations are stable. Allylic and benzylic carbocations are very stable. So for example, if we look at something where we have an alkene that is adjacent to an aromatic ring, this is known as styrene. This electrophilic addition reaction is quite fast because after protonation of the alkene, we have a carbocation that is benzylic, which means it is very stable. As a result, this carbocation is very quick to form, this reaction is very fast, and the carbocation can then be attacked by our nucleophile, which is the bromide ion, to generate the electrophilic addition product. If you can form a carbocation that's allylic or benzylic, that carbocation is going to be very stable and very easy to form. By the same token, if we have this diene, let's try to draw some products. So if we protonate the alkene, that in turn will generate a carbocation. Now, if we have a choice at protonating at position A or B, we're going to protonate at position A because it generates a carbocation that is allylic. So we prefer to generate the more stable allylic carbocation. From there, your nucleophile, which is the bromide anion, will attack and in turn generate your substitution product. Sorry, will in turn attack and generate the electrophilic addition product. Now, for those wondering, can't we delocalize this carbocation? Yes, but we'd get the exact same product for this molecule. We'll talk more about electrophilic addition for conjugated systems in later chapters. For now, the key thing I want you to keep in mind is that if you can generate an allylic or benzylic carbocation, those are very stable, very easy to make, and you have fast, efficient electrophilic addition reactions. Now, you may be wondering, how do we know that we're actually going through a carbocation? Well, we have some evidence in terms of kinetic studies, but we also see evidence for carbocation intermediates by virtue of the fact that we observe alkyl and hydride shifts for these electrophilic addition reactions. Carbocations can undergo alkyl and hydride shifts to give the most stable carbocation. For example, if you take 3-methyl-1-butene, protonation of the alkene generates a secondary carbocation. Unfortunately, you start to see some hydride shifts, and a hydride shift occurs to make a more stable tertiary carbocation. Thus, you see a mixture between the secondary and tertiary chloride product. So, whenever you deal with electrophilic addition, you got to be really careful and always cognizant of the possibility that once you make your carbocation, it can undergo hydride or alkyl shifts, and you can end up with your halogen on an entirely different carbon than maybe what you intended. So, to this end, let's draw a mechanism for the following reaction. So in this case, we have our alkene, and somehow we end up with your halogen installed at the adjacent tertiary position. This is an immediate signpost that some sort of alkyl or hydride shift has occurred. So in drawing the mechanism, I'd like you just to take a few moments, draw the step-by-step mechanism to show how you go from this reactant to this product, and then we'll discuss momentarily. So first and foremost, we protonate the alkene. If we want to generate the carbocation, we'll prefer to generate at the more stable secondary position. Once we have our carbocation generated, we're going to observe a hydride shift, in which we have a shift of a carbon-hydrogen bond to generate a new carbocation. Why does this occur? We can generate a much more stable tertiary carbocation, which can then be attacked by our bromide anion, and that in turn generates the desired product. So, just whenever you're dealing with electrophilic addition, be careful and always think about the possibility that hydride or alkyl shifts can occur. Okay, let's talk about the stereochemistry of electrophilic addition. So carbocations are planar, flat, and thus the nucleophile can approach from either face. A carbocation is flat. It is sp2 hybridized, and it can be attacked by nucleophiles from either the top or the bottom face. As a result, we get a mixture of stereoisomers for alkene hydrohalogenation. Functionally, you get a racemate, which is an equal mixture of stereoisomers or enantiomers. One thing I would like to note is the stereochemistry of alkene addition can be biased if there is steric hindrance on one face of the molecule. For example, in the following substrate, the top face is blocked by this large group, and thus addition exclusively occurs from the more accessible bottom face of the molecule. This is an example of facial selectivity and substrate selectivity. Now, we've been talking primarily about hydrohalogenation, but for electrophilic addition, we can use other nucleophiles. So water can react with alkenes under acidic conditions to yield alcohols. So in this case, just like before, we protonate the alkene to generate the more stable carbocation. And from here, water, as our nucleophile, can attack the carbocation to form an oxygen-carbon bond. The one thing that's new is you have to do a cleanup step where you pull off this proton to generate your neutral alcohol. As you can see, if we treat an alkene with water under acidic conditions, we end up installing the alcohol at the most substituted position with Markovnikov regio control. So to practice drawing this mechanism, let's try with this alkene substrate. So we have a primary and secondary position. We're going to protonate to generate the carbocation at the more stable secondary position. From here, water is a competent enough nucleophile to attack our carbocation. That in turn generates the following molecule. Now remember, because we're dealing with water, we have one more cleanup step where water pulls off a proton so that we get our neutral alcohol. So as you can see, net overall, we've installed this alcohol at the most substituted position. So let's try to predict the products of the following reaction, and I'd like you to draw each enantiomer formed. Keeping in mind that because we go through a carbocation, we're going to get a mixture of enantiomers and a mixture of stereoisomers. So pause the video, take a few moments, and let's draw the predicted products for this reaction. So first and foremost, if I have H3O plus floating around, we're going to protonate the alkene. That means we're going to get the carbocation at the most substituted position. From here, water is going to attack. It can attack from either face, and thus we would get a mixture of stereoisomers and a mixture of enantiomers. I'm going to draw these alcohols after the cleanup step just to show and to save some space. So because the water molecule can attack from either the top or bottom face, we get a mixture of the two possible enantiomers. One where the water molecule comes in from the top, the other where the water molecule comes in from the bottom face. Now, in addition to intermolecular reactions, we can also have intramolecular reactions. So in this case, rather than having an external nucleophile like water, we have an internal nucleophile, such as an internal alcohol. With that hint in mind, I'd like you to take a few moments and to try to draw a mechanism for the following reaction. In net, we formed a bond between this carbon and our oxygen atom. So let's draw a mechanism that accomplishes that. So pause the video, work through this example, and then we'll discuss. So first and foremost, we're going to protonate the alkene. You can just draw it using H+ in this case. One, two, three, four, five. 1, 2, 3, 4, 5. And now we have the alcohol. From here, the alcohol will attack the carbocation internally. And from here, as a cleanup step, either water or another equivalent of our alcohol will come in and pull off this proton, which in turn will generate our final product. We can redraw this after rotation to look like this. There we go. So this case, instead of water, we had an internal nucleophile, such as an alcohol, attack the carbocation. Okay, so we talked about alkene hydration under acidic conditions. Let's now move on to another class of reaction, which is the addition of halogens to alkenes via halogenation. So halogenation proceeds through concerted formation of a three-membered halonium ion, followed by ring opening of the halonium ion by attack on the most substituted carbon. The halonium ion is formed with syn stereochemistry, and ring opening gives the anti-dihalide. Because the halonium ion can form on either face, a mixture of enantiomers is generated. Alkene dihalogenation is the first example of both a three-membered ring intermediate, in the case of the halonium ion, and ring opening to yield an anti-product. So in terms of the mechanistic steps, first we end up with attack of the alkene onto the electrophilic bromine atom. This generates the bromonium ion. From here, the bromonium ion is attacked from the opposite face by a second equivalent of the halogen, which is the bromide anion. The bromide anion opens up the bromonium ion, and that yields the dihalide. The dihalide is formed with anti-stereochemistry, and as a result, both halogens are on opposite faces of the molecule. We get a mixture of enantiomers as the bromonium ion can form on either the top or bottom face. So as some additional practice, let's practice this mechanism on the following substrate. So first, we cyclize and form our bromonium ion. I'm going to arbitrarily form the bromonium ion on the top face. You can just as easily form it on the bottom face. From here, your equivalent of bromide will attack and open the bromonium ion at the most substituted carbon. In this case, we're going to attack with the bromide anion and open the bromonium ion at the tertiary carbon position. That in turn yields the dihalide. And as you can notice, both of the bromine atoms are installed on opposite faces. We also observe the enantiomer, which occurs if the bromonium ion forms from the opposite face on the bottom. And so here's the enantiomer. As you can see, these two do represent an actual pair of enantiomers with the opposite configuration at every stereocenter. One thing I'd like to note is that the first step, the concerted formation of a three-membered ring, is a key step in many alkene reactions. So I'd like you to take a moment now, and we're going to look at a Z and E alkene. And what I would like for you to do is for this Z and E alkene, I'd like you to predict the products of the following reactions, and I'd like you to draw all enantiomers formed. So pause the video, work through these examples, and then we'll discuss momentarily. So first and foremost, we're going to form a bromonium ion. From here, when you generate this bromonium ion, your methyl groups will both be in the back, and the hydrogens will be in the front. Okay, from here, this bromonium ion can be opened up. In this case, both sides are equally substituted, so we don't have anything to worry about there. So we're going to open up the bromonium ion from the opposite face, and that in turn yields the following. So let's draw this first without dash wedge, just to see what's happening here. So as we can see, the two bromine atoms are on opposite faces of our molecule. We can draw that out if we keep the carbon chain just as is, with one of the bromine atoms with a wedge, the other bromine atom with a dash. You also observe the enantiomer in this case. Let's now look at the E alkene, where we have many similarities, but there's one thing you're going to have to look out for and be very careful for. So we're going to make the same bromonium ion, except this time the two methyl groups are on opposite faces. One methyl group is pointing towards the front, the other is in the back. We are going to open up the bromonium ion, and we can open at either carbon since both are equally substituted. Opening of the bromonium ion gives us the following I'm going to draw it in this rudimentary way before I add in the dash wedge notation. Okay. So, as we can see in this case, we have the two bromine atoms on opposite faces. Like so. Now, before you go and put plus enantiomer on here, if we rotate our carbon-carbon bond, this is equivalent to the following depiction. Now, does anyone see a problem with putting plus enantiomer here? The main problem is that this product is meso. So we only get one product out from this reaction. You don't get a mixture of enantiomers. Both of the enantiomers that you generate are identical. So this is why it's important to be very careful whenever you generate and whenever you have a symmetrical substrate, just to make sure you aren't accidentally generating a meso product. Now, one thing I'd also like you to note, part of the reason we looked at both an E and Z alkene as those are the only two possible alkenes you could deal with. So if you know the stereochemical outcome for an E and Z alkene, you can in turn predict the products for pretty much any alkene reaction. So because we know the outcome for an E and Z alkene reaction under dibromination conditions, this is general to any E or Z alkene that we encounter. The other thing I'd like you to note is the alkene geometry and the alkene stereochemistry directly impacts the product stereochemistry. These reactions are stereospecific. If you start with a Z alkene, you get a defined product out. You start with an E alkene, you get a different but defined product out. Wonderful. Let's talk about a variant of halogenation, which is halohydrin formation. The bromonium and halonium ion intermediate can be intercepted with other nucleophiles, such as water, alcohols, and internal nucleophiles. So if water is used as a reagent or co-solvent during halogenation, a halohydrin is formed. So this time, instead of a second halogen being installed, you install an equivalent of water or hydroxide. Now, rather than just using bromine, chlorine, or iodine, oftentimes N-bromosuccinimide, NBS, is used as a Br plus equivalent that avoids competing addition of bromine to the alkene. Mechanistically, halohydrin formation is very, very similar to dibromination or dihalogenation, in that in the first step, you generate a bromonium ion where Br plus adds to either face of the alkene. From there, once you have your bromonium or halonium ion, water attacks from the opposite face of the bromonium ion at the most substituted carbon or the carbon that has the most cationic character, yielding the anti-addition product. Once you generate your alcohol, the alcohol is deprotonated by solvent to generate the halohydrin. So, just to showcase this mechanism, in the first step, you cyclize to make a halonium ion. From here, water attacks the, in this case, bromonium ion from the opposite face at the most substituted carbon. Once you've generated this addition product and water has attacked and opened your halonium ion, your protonated alcohol is deprotonated by succinimide or solvent, and in turn, you get your halohydrin. Let's do some more practice in drawing the mechanism for this reaction. So in this case, we have the following alkene. This is in this case, this would be an E-alkene. So again, first you cyclize to make a bromonium ion. From here, water is going to attack and open the bromonium ion at the most substituted position. If we have a choice between position A and B, position B is more substituted, and as a result, it can in turn stabilize and accommodate a partial positive charge more readily, and thus the more substituted position is attacked, and that opens up the bromonium ion from the opposite face. This in turn generates the following addition product. So converting this to dash wedge, the bromine is pointing up, the methyl group is pointing up, the alcohol is pointing down. And the hydrogen is pointing down. Okay, so now that we have that sorted, we only have one last step. Water is going to pull off a proton, and that in turn generates our final product. Okay, perfect. So again, for halohydrin formation, you generate your bromonium ion. The bromonium ion gets opened up by water at the most substituted carbon, and then the alcohol is deprotonated. You will also generate the enantiomer, which occurs if the bromonium ion forms on the bottom face. Okay, let's talk about a variation of halohydrin formation, and let's talk about how halohydrin formation functions in terms of Markovnikov's rule. So halohydrin formation follows Markovnikov's selectivity, favoring addition of the alcohol or water at the most substituted carbon that can most readily stabilize a positive charge. Even though you aren't making a carbocation, you still have to consider which carbon is most substituted and which carbon can stabilize a partial positive charge. So in this case, if you have a choice between a primary or a secondary benzylic position, the addition of water will occur selectively at the secondary benzylic position. Again, although a formal cation is not generated, the carbon-bromine bond attached to the carbon that can more readily stabilize a positive charge is weaker and more reactive towards displacement. So as you can see here, if we compare the primary versus the tertiary position, the more substituted tertiary position can more readily stabilize a partial positive charge, and thus we observe it has a longer, weaker bond. For example, here, if we have a choice between a tertiary and secondary position, attack and opening of the bromonium occurs selectively at the more substituted tertiary position because this carbon-bromine bond is weaker. Now, one variation of halohydrin formation is haloetherification. Polonium intermediates can react with alcohols or other internal nucleophiles. So in this case, rather than water, we're using an alcohol. The mechanism otherwise is exactly the same. So let's practice and let's try to draw a mechanism for this reaction. So pause the video, work through this example, and then we'll discuss. Okay, so first and foremost, we're going to need to generate and we're going to need to form a halonium ion. This time we're using chlorine rather than bromine, but the mechanistic step is identical. I'm going to suppose that we're going to generate the halonium ion from, in this case, because the chlorine ends up on the bottom, let's just have the halonium ion on the bottom face. From here, our nucleophile, which is just any generic alcohol, will attack and open up the halonium ion. We're going to open up the halonium ion at the most substituted carbon from the opposite face. So because the halonium ion's on the bottom face, the alcohol ends up on the top face, and the chlorine ends up on the bottom face. So as you can see, the alcohol and the chlorine atom are anti to one another. From here, as a cleanup step, one of the alcohols is going to deprotonate, pull off a proton, and that in turn gives us our neutral haloetherification product. Of course, plus the enantiomer. Wonderful. So one last variation of haloetherification are intramolecular reactions. So internal nucleophiles can react with halonium ion intermediates. And importantly, the stereochemistry of the nucleophile can influence the stereochemistry of the products generated. This is a classic motif used in a lot of natural product syntheses, where you use the stereochemistry found in one part of the molecule to transfer information to other parts of the molecule. So in this case, we can generate a halonium ion. And because this group is on the top face, when we generate the halonium ion, it will selectively react with the group on the top face. And in turn, we get an internal haloetherification. So we formed a new carbon-oxygen bond, but this bond was formed with not only regio control, not only stereospecificity, but we also get product-driven stereoselectivity. Really powerful stuff. So, given that example in mind, I'd like you to draw a mechanism for this reaction, and I'd like you to predict the stereochemistry of the products from this reaction. So in this case, we have an alkene, we have an internal alcohol, and we are treating this alkene with N-bromosuccinimide and water, and I'd like you to take a few moments to predict the products and draw a mechanism for this reaction. I'd like you to note that the nucleophile in this case is going to be the internal alcohol. So, in discussing this, first and foremost, for N-bromosuccinimide, N-bromosuccinimide looks a little bit like this. We're going to get cyclization in turn to generate a halonium ion. What I'm going to do before I draw out the halonium ion is I'm going to redraw this molecule. In a way that makes it easier for us to see that final ring closing step. So when we generate this halonium ion, we're going to generate the halonium ion, in this case, arbitrarily on the bottom face. From here, the alcohol is going to open up the halonium ion. And in this case, we have a choice between the two positions because they're both secondary. If you have a choice between forming a 5 or 6-membered ring, you'll get a mixture, but generally 5-membered rings are slightly preferred, but we'll draw the 6-membered ring route. From here, after ring opening, we generate this cyclic species here. We open up our halonium ion. And that in turn gives us the following product. Noting that the halonium ion and the bromine atom are on opposite faces. You will also observe the enantiomer as well. Key thing I want you to keep in mind is that intramolecular reactions can occur, and it's important to know how to draw the mechanism for those intramolecular reactions. One last thing as a cleanup step, because this alcohol is still protonated, we're going to pull off this proton, and that in turn generates our final product. Let's do some more practice now. And given that an alkene can be either cis or trans, let's predict the product for each type of alkene. So take a few moments, let's work through this example, and then we'll discuss. So we have an E and Z alkene. So let's predict the product for halohydrin formation given an E and Z alkene. So first and foremost, if we have a Br plus equivalent, we're in turn going to generate a halonium ion. From here, water is going to open up the halonium ion from either face. And in turn, we can generate the following mixture of products. Okay, so we've discussed what occurs for the E alkene. So we generate the bromonium ion, we open up the bromonium ion. In the end, the bromine and the alcohol end up on opposite faces. That should be a hydrogen, and this is our CH3 group. Okay, perfect. Let's look at the second case for the Z alkene. Just like before, we're going to generate the bromonium ion. The bromonium ion is going to get attacked and opened up by water. In this case, we can attack on either side since they're equally substituted. And that in turn generates the following ring opening product. The major difference being that this time the CH3 groups are on the same side. So if we wanted to redraw this a little bit nicer, it would look like this. If we wanted to show the difference, we can rotate this bond and I can redraw the Z alkene product in the exact same way as the E alkene product to really help you see what's happening here. So here, if we draw these two molecules the same way, what we see is that depending on whether we have an E or Z alkene starting material, we see a different stereochemistry observed in our two products. So, as you can see, once again, because we discussed both an E and Z alkene, if you know the products for the reaction of an E and Z alkene, we've essentially covered any possible alkene you'd encounter, because an alkene will either be E or Z or polysubstituted, which we discussed earlier. Okay, so let's keep going now, and let's talk a little bit about alkene oxidation in terms of epoxidation. So in discussing alkene oxidation, epoxidation, alkenes can be converted to epoxides with syn stereochemistry using peroxy acids such as MCPBA or metachloropurbenzoic acid. So in this case, we've taken an alkene and we can convert it to an epoxide. We get a mixture of epoxide and enantiomers, but the epoxide is installed with syn stereochemistry. This is another concerted mechanism where we have concerted formation of the epoxide in a single step. So in this case, first and foremost, we have cyclization to form two carbon-oxygen bonds. We break the peroxy acid oxygen-oxygen bond. We abstract a hydrogen, and this. So in essence, what's happening here is we are forming two carbon-oxygen bonds, and we are breaking the peroxy acid oxygen-oxygen bond. This entire set of arrows occurs as part of a single mechanistic step. This is a concerted reaction. Here's what the transition state looks like. And net, we install the epoxide in a concerted manner on a single face of the alkene. Now, epoxidation is stereospecific, where the reactant stereochemistry dictates the product stereochemistry. For example, in this case, if we have an E-alkene, we end up with an epoxide where the hydrogens are trans to one another. By the same token, if we have a Z-alkene, we end up with an epoxide with the two hydrogens cis to one another. So, what I want you to do now is I'd like you to predict the products of the following reaction, and I'd like you to draw a mechanism for this reaction, where MCPBA, or metachloropyroxybenzoic acid, looks something like this. The key point being is that the reactive part of the molecule that we all care about is the peroxy acid payload at the end of the molecule. So I'd like you to pause the video now, take a few moments, and I'd like you to draw a mechanism for this reaction, and I'd like you to predict the products for this reaction. Okay, so let's discuss now. So in this case, in terms of the concerted reaction for this alkene, I'm going to draw out MCPBA just in a way that's a little bit closer to the alkene to make it easier for me to draw the concerted mechanism. So in the concerted mechanism, we end up with the attack onto the electrophilic oxygen atom. And I'm going to show you another way that your textbook likes to draw the arrows. So first you draw an arrow from the alkene to the oxygen. You break the peroxy acid oxygen-oxygen bond. You then abstract a hydrogen, and it's this set of electrons that's used to form the second oxygen-oxygen bond. This is the way that your textbook draws this concerted mechanism, and both ways of drawing the arrows are fine. Net, we end up with just the metachlorobenzoic acid, as well as, most importantly, the epoxide product. And in this case, the epoxide oxygen atoms installed in a syn manner. Both of the carbon-oxygen bonds are on the same face. And as you can see in our initial alkene, the hydrogen and methyl group are cis on the same side, and that's retained in the product. Just like the methyl and ethyl group are on the same face, and that's retained in the product. You get the following product plus its enantiomer. To show you what the enantiomer would look like, it would entail the oxygen being installed on the bottom face. Okay, so we've practiced drawing out epoxidation mechanisms. Let's look at another way that we can use these epoxides. So acid-catalyzed epoxide opening is a really useful process to make diols and ethers. In acid-catalyzed epoxide opening, it proceeds with Markovnikov selectivity and anti-stereochemistry. So if epoxide opening is performed with an alcohol nucleophile, the nucleophile is incorporated at the most substituted position anti to the epoxide hydroxyl group. So, as we can see, the alcohol from the epoxide and the incorporated OR group are anti to one another. Additionally, the incorporated OR group, the alcohol that we use to open the epoxide, is installed in a Markovnikov regiochemistry. It's installed at the most substituted position. To help explain why that is, let's look at the mechanism. So first, we activate the epoxide. So the epoxide is protonated. Now that we have this protonated epoxide, we can open it. This is very similar to the bromonium ion intermediate that we looked at previously. We can open up this cyclic protonated epoxide, and in this case, our nucleophile is going to attack at the most substituted position. So we end up with attack and opening of our epoxide. As you can see, because epoxide opening occurs from the opposite face to the epoxide carbon-oxygen bond, the two alcohols are installed anti to one another. The last step in the mechanism is a deprotonation to generate a neutral diol product. Okay, so let's try to practice drawing a mechanism for this reaction, and let's predict the products of the following reaction. And I'm going to tell you right now that this substrate is exactly the same as what we looked at in the prior example. And at the end of step 1, we noted we had the following epoxide product. Now, what happens if we treat this epoxide with acid and methanol? Take a few moments, work through this example, and then we'll discuss. Okay, so first and foremost, we're going to protonate our epoxide. This activates the epoxide and ensures that we're under the acid-catalyzed regio control and stereo control model. From here, our nucleophile, which is methanol, is going to attack and open the epoxide from the opposite face. That in turn generates the following epoxide opening product. Now, before we assign dash wedge notation in its entirety, it's important to note that the alcohol is pointing towards us, and so this OH group is pointing towards us. The methanol added from the opposite face. So if the alcohol has a wedge, this methanol group will have a dash. To provide a 3D drawing of this to help you see what's happening, and you can also make a model to showcase this. One way that I like to visualize this opening is to think about it from the perspective of like a Newman projection. So here's our epoxide. In this case, we have the ethyl group and methyl group. Here we have in the back the methyl group and a hydrogen. We open the epoxide, and that in turn, after opening, gives us something that looks like this. So as we can see post-opening, if we're just treating these methyl groups as part of the main chain, we see that this alcohol and the ethyl group are on the same face, so they get a wedge, while the methanol and hydrogen are on the same face and they get a dash, which matches our dash wedge depiction. You can also make a model to verify this. I just wanted to provide you a justification and another method to help visualize stereochemistry beyond just drawing the lines, noting that the alcohol and installed methanol group are on opposite faces, and assigning dash wedge from there. So, as one last cleanup step, after epoxide opening, we're just going to pull off this proton, and that generates our neutral alcohol product. So as you see, we had a Z alkene in this case. And our final product, we also generate along with its enantiomer. So in summary, you make your epoxide, the epoxide gets protonated, the epoxide is opened up from the opposite face to the epoxide on the most substituted carbon, and that in turn gives us the anti-addition product. Okay, let's keep going now. And let's talk a little bit about nucleophilic epoxide opening that I like to call, and that's commonly referred to as the SN2 pathway. So in nucleophilic epoxide opening under basic neutral conditions proceeds through what's known as an SN2 pathway. Under basic and neutral conditions, the nucleophile is going to attack the least substituted carbon, and the reaction does not occur for tertiary carbons under basic and neutral conditions. As this is an SN2 reaction, the nucleophile net attacks with anti-Markovnikov regiochemistry and yields the anti-stereochemistry product. So, the key mechanistic difference between acidic and basic conditions is under basic conditions, it's an SN2 reaction. And what that means is you're going to attack and open the epoxide from the opposite face at the least substituted position. So as you can see, if we compare a tertiary and secondary position, because we're under basic SN2 conditions, basic neutral conditions, our nucleophile is going to attack and open the epoxide at the least substituted secondary position. This gives you the anti-Markovnikov product. However, as we note, the net stereochemistry is still anti. After epoxide opening, because you have this alkoxide ion, you're going to protonate the alkoxide ion using water or another proton source that's floating around solution. One thing I'd like you to note is one benefit of epoxide opening under basic neutral conditions is a range of nucleophiles can be used, such as alkyl lithiums, alcohols, amines, and hydrides. So here's an example with an alkyl lithium where if we have a choice between the most and least substituted position, this alkyl lithium will attack the least substituted position and open the epoxide from the opposite face. So as you can see, the epoxide initially had a wedge, and so the alkyl lithium attacks from the opposite face. The alkyl lithium gets a dash. You can also use something like sodium methoxide. In this case, again, we attack and open the epoxide from the least substituted position on the opposite face to the epoxide. With this discussion in mind, let's try to predict the products of the following reaction, keeping in mind that we've already done step 1 for this reaction, and you can start and draw this reaction from the perspective where you start with this epoxide and go from there. So here's an epoxide that we're going to be starting from. Again, epoxidation occurs in a concerted manner, and here in this case, we have an E-alkene. Here's the epoxide that we generate, and I'd like you to tell me what happens when we treat this with sodium methoxide in methanol. So take a few moments, pause the video, and then we'll discuss. So in this case, the nucleophile, which is methoxide, is going to attack and open the epoxide from the opposite face at the least substituted carbon. So we're going to attack the least substituted secondary position and open up this epoxide. From here, as a cleanup step, we're going to protonate the alkoxide, and that in turn generates our neutral product. We get this product along with the enantiomer. Okay, let's keep going now. And let's talk about another concerted reaction, and this involves alkene cyclopropanation. So carbenes react with alkenes to generate cyclopropanes. The cyclopropane is formed with syn stereochemistry. How do we get a carbene? A carbene can be generated from methyl iodide and zinc copper alloy, or diazomethane and light, or heat. So what is a carbene? A carbene looks like follows. It is neutral. However, this carbon has both a lone pair and an available empty p orbital that it can use for reactions and bonding. Cyclopropanation is a concerted reaction where the carbene both attacks the alkene and is attacked by the alkene. And net, we form two carbon-carbon bonds, and that gives our cyclopropane ring. This is another example of a concerted reaction to make a three-membered ring, similar to epoxidation and formation of a bromonium ion that we discussed previously. Cyclopropanation is stereospecific, and the alkene stereochemistry dictates the product stereochemistry. So for example, in this case, we have an E-alkene. The hydrogens are opposite to one another. They're trans to one another. In the product, cyclopropane, the hydrogens are still trans to one another. If we have a Z-alkene with the hydrogens cis to one another, in the product, the hydrogens are cis to one another. So in this case, I'd like you to predict the products from the following reaction and draw a mechanism. So in this case, we have a Z-alkene. So I'd like you to pause the video and tell me what the product is going to be for this reaction. Okay, so first and foremost, Treatment of, in this case, diiodomethane with zinc copper alloy generates a carbene. Next, we're going to see concerted formation of the two carbon-carbon bonds. So our cyclopropane carbon is installed in a syn fashion. We start with our two hydrogen atoms cis to one another. In the product, the two hydrogen atoms are cis to one another. Now, in this case, we only get this single product because it's perfectly symmetrical. This is a meso compound. So you don't put plus an enantiomer in this case because it's identical to its enantiomer. Okay, let's keep going now, and let's talk about the preparation of dichlorocyclopropanes from alkenes. As we discussed, carbenes can be prepared from diazomethane under irradiation. So in this case, you break the carbon-nitrogen bond, you release nitrogen gas, and you get your carbene. We can also make dichlorocarbenes, which is prepared from chloroform and sodium hydroxide. In this case, you deprotonate chloroform, and from there, you lose your chloride leaving group, and you get a dichlorocarbene. Dichlorocarbenes and other dihalogenated carbenes can react with alkenes to make dichlorocyclopropanes with syn stereochemistry. Key difference being you have these two chlorine atoms. The mechanism is identical to cyclopropanation using the methyl or using the CH2 derived carbene. So let's practice and let's try to predict the products from the following reaction and draw a mechanism for this reaction. So this time we have an E-alkene. Note, in the prior example, we did a Z-alkene. Let's look at an E-alkene now. In this case, we're treating it with chloroform and sodium hydroxide. So take a few moments to draw out the mechanism for this reaction and the products, and then we'll discuss. Okay, so first and foremost, we need to make a carbene. So easiest way to do that, because we have chloroform, first, hydroxide is going to pull off this proton. Chloroform is somewhat acidic. From here, you lose your leaving group, and we now have our dichlorocarbene. The dichlorocarbene is going to selectively react with, in a concerted manner, our alkene, and that in turn generates our dichlorocyclopropane. Notice that in this case, the ethyl groups are on opposite faces to one another. This molecule is not meso, it is not symmetrical. So this, we get a single product plus it's an enantiomer. Okay, let's keep going now. And let's talk about another class of reaction that goes through a three-membered ring intermediate. Here we're going to be talking about oxymercuration. So hydration of an alkene through a two-step process of oxymercuration followed by reduction. So we can take an alkene, treat it with mercury acetate and water. That generates and incorporates and forms a carbon-oxygen bond as well as a carbon-mercury bond. And then we can then convert this compound into a typical alcohol by treatment with borohydride. Net, we've taken an alkene and we've converted it to an alcohol with Markovnikov regiochemistry. Let's look at the mechanism to explain why. First and foremost, we have concerted formation of a mercurinium ion. This is going to look very similar to formation of a bromonium ion. This mercurinium ion can then be attacked and opened up by nucleophiles such as water. The attack occurs at the most substituted position that can most readily stabilize a positive charge. This ring opening results in the alcohol and mercury atom being anti to one another. As a cleanup step, the alcohol is deprotonated. Now, this alkyl mercury species can be isolated, but usually it gets reduced with borohydride and in turn generates just a normal alcohol. Demercuration follows a radical mechanism, and this demercuration step is not stereospecific. You get a mixture of stereoisomers at that center. So, for example, if we take this alkyl mercury species and we treat it with sodium borohydride or a deuterated sodium borohydride, what you notice is that the reduction of the alkyl mercury species yields a mixture of enantiomers. So the reduction step is not stereoselective or stereospecific. When we talk about oxymercuration, let's talk about some reasons why we would use oxymercuration compared to, for example, acid-catalyzed hydration. So as a net result of oxymercuration, an alkene is converted to an alcohol with Markovnikov regiochemistry. This can also be accomplished via acidic hydration, but not for every substrate. Oxymercuration is particularly useful in that it is used to avoid rearrangements observed under strongly acidic conditions. For example, if you take the following substrate and try to install an alcohol at this secondary position, you'll instead end up with carbocation rearrangements because once you get a carbocation at this position, you will observe an alkyl shift and ultimately you won't get the product that you want due to these alkyl shifts. With oxymercuration, you don't have that problem because you don't go through a carbocation. We go through a mercurinium ion. And because we go through a mercurinium ion, we don't see carbocation rearrangements. So the main use of oxymercuration is that it can be used on sensitive substrates. Let's try to practice what we've learned, and I'd like you to draw a mechanism for the first step in the following reaction. And I'd like you to predict the products for this oxymercuration reaction. So pause the video, take a few moments, and then we'll discuss. So in this case, we are treating this alkene with mercury acetate and water. So in the first step, we're going to make our mercurinium ion. From here, water is going to attack and open up the mercurinium ion and the opposite face at the most substituted carbon, the carbon that can most readily stabilize a positive charge. Notice that the mercury atom and the alcohol are installed anti to one another, though that stereochemistry is going to get obliterated in the next step, unfortunately. Once we have this alkyl mercury species, treatment with sodium borohydride via a radical mechanism reduces the alkyl mercury, giving us a racemic mixture of reduction products. So here we get the following product. We don't have to put plus enantiomer because this molecule is symmetrical. This is not an actual stereocenter. So always just check before you put plus enantiomer that you're actually getting a mixture of enantiomers. Okay, let's talk a little bit about some variations of oxymercuration, one of which is a variation used to prepare ethers. So if an alcohol is used instead of water, an ether is formed with Markovnikov regioselectivity. So for example, if we use methanol instead of water, you see that we install the methanol-derived ether at the most substituted position. Let's draw a mechanism for this reaction, and as a hint, the alcohol is the nucleophile. So not much has changed, really. The first step is still exactly the same. We form our mercurinium ion. And from here, this time our nucleophile is methanol. It's going to open up the mercurinium ion. And as our final cleanup step, another equivalent of methanol is going to pull off a proton. And from here, after treatment with sodium borohydride, we're going to reduce off this alkyl mercury, and that leaves us with this methanol-derived ether as our product. Really, it's the exact same mechanism. We just are using an alcohol such as methanol instead of water. Another variation of oxymercuration is an intramolecular variant, where it can be used to prepare cyclic ethers via an intramolecular reaction. So in this case, we have an internal nucleophile, such as this alcohol, and it's being used to form the following carbon-oxygen bond. Let's draw a mechanism for this reaction. So as always, what I'm going to do before I do anything is I'm going to draw out my molecule in a way that makes it easier for me to draw out the cyclization step. As always, in the first step, we're going to form the mercurinium ion. From here, we're going to open the mercurinium ion at the most substituted carbon. And that in turn is going to make a 1, 2, 3, 4, 5-membered ring. As a cleanup step, another equivalent of alcohol or water, or an equivalent of acetate that was kicked off during this reaction, will pull off this proton. And from here, treatment with sodium borohydride will generate our desired cyclic product. Again, the only difference here is we're using an internal nucleophile. Okay, let's keep going now. And we're moving on to a new class of what I like to call concerted alkene reactions. In this case, we have hydroboration-oxidation. So hydroboration-oxidation of alkenes yields an alcohol with anti-Markovnikov regiochemistry. The alcohol is installed at the least substituted position. The addition of borane and hydride is concerted, yielding a syn addition product. Importantly, boron and hydride add to the same least hindered face of the alkene with syn stereochemistry. And boron, because it's installed at the least substituted carbon, the alcohol ends up at the least substituted carbon. So for example, if we treat the following alkene with BH3, or in this case, borane, and sodium hydroxide hydrogen peroxide, which oxidizes the boron atom, you get the alcohol product with syn stereochemistry and anti-Markovnikov regiochemistry. The alcohol is installed at the least substituted position. What's the mechanism that explains this? First, you have concerted addition of boron and hydride to the alkene. The boron, again, is installed at the least substituted position. And the boron and hydrogen are installed syn to one another on the same face. In terms of the oxidation mechanism, the oxidation occurs with retention of stereochemistry. I will show you this oxidation mechanism, but you won't have to draw this full mechanism on an exam, but you should be familiar with how it works. The key thing to take away is the oxidation occurs with retention of stereochemistry. So in the first step, we deprotonate hydrogen peroxide. Next, we have the attack of peroxide onto boron. From here, you have a rearrangement where the alkyl group shifts over and we break the oxygen-oxygen bond. Finally, we hydrolyze the boron-oxygen bond, yielding an alkoxide ion, which is then protonated to yield our final alcohol. Net hydroboration oxidation installs a hydrogen and alcohol with syn stereochemistry, and the alcohol is placed with anti-Markovnikov regiochemistry on the least substituted position. Now, it's important to note that hydroboration oxidation is another example of a stereospecific reaction. If you start with an E-alkene, you get a defined product stereochemistry. If you start with the Z-alkene, you get a diastereomeric product. As you can see, if you change the alkene stereochemistry, you change the product stereochemistry. So let's try to now apply what we've learned, and let's try to predict the product of some reactions. So in this case, we have the following alkene. I'd like you to predict the product for this reaction and draw a mechanism for this reaction. So in this case, we're taking the following alkene, treating it with B2H6, followed by hydrogen peroxide sodium hydroxide. To make this example a little bit more interesting, let's make this group a hydrogen and this group a methyl group. So I'd like you to tell me what's the product of this reaction, and let's draw a mechanism for this reaction. So pause the video and we'll work through and discuss this example momentarily. Okay, so first things first, we end up with concerted addition of boron and hydrogen. The boron is installed at the most substituted carbon. The hydrogen's installed at the least substituted carbon. The addition occurs with syn stereochemistry. So the boron and the hydrogen atom end up on the same face. Treatment with hydrogen peroxide and sodium hydroxide oxidizes the boron atom to yield an alcohol. Net, the alcohol is installed at the least substituted position, syn to the hydrogen. This yields the following product, plus its enantiomer. One other thing that I'd like to note is that hydroboration, you can observe substrate selectivity in hydroboration-oxidation reactions. For example, in the following molecule, the top face approach is less hindered, so you see almost exclusive hydroboration and addition of hydrogen and boron from the top face. This is one case where you can get substrate-controlled selectivity of hydroboration-oxidation products by virtue of the fact that hydroboration-oxidation is very sensitive to steric hindrance. Let's talk about another concerted mechanism. In this case, this is alkene reduction via hydrogenation. So alkenes can be reduced with hydrogen, facilitated either by palladium carbon or a platinum catalyst. Alkene reduction with hydrogen occurs with syn addition of hydrogen. So both of the hydrogens are installed on the same face. In terms of the full mechanism, because it's metal mediated, the mechanism can often be dependent on the exact catalyst that you use, but here's a general framework. First, hydrogen adsorbs onto the metal catalyst and is bound to the metal catalyst. On the catalyst surface, hydrogen dissociates into individual. You break this hydrogen-hydrogen bond and we get hydrogen atoms bound to the metal catalyst surface. The alkene adsorbs to the catalyst surface. From there, hydrogen is successively transferred onto the alkene, and the reduced product then dissociates off of the metal catalyst surface. Again, to note, hydrogenation yields the syn addition product, and hydrogen adds from the least hindered face. With that in mind, let's take a look at a set of alkenes. In this case, we have a Z-alkene. In the second case, we have an E-alkene. And let's predict the product for hydrogenation of these two alkenes. So take a few moments to work on this example, and then we'll discuss. So in this case, we have concerted syn addition of hydrogen. Even though this isn't the actual mechanism, you can draw it like a concerted addition. So here we have the two hydrogen atoms installed on the same face. So if they're installed on the top face, that gives the hydrogen both wedged, and we'll have the ethyl groups both dashed. We don't have to put plus enantiomer because this guy is a meso product. By comparison, if we have an E alkene, the hydrogens are both installed on the same face, but this time the ethyl groups are on opposite sides of the molecule. This molecule is no longer perfectly symmetrical. So this one, you get this product plus the enantiomer. Wonderful. Let's keep going now. Here's another concerted or syn addition reaction, and this is alkene dihydroxylation. Treatment of alkenes with osmium tetroxide and NMO, which is a oxidizing reagent, followed by potassium hydrogen sulfite, yields the syn diol product. So here's what osmium tetroxide looks like, and NMO is just an oxidizing agent to turn over your catalyst, because you typically don't want to use stoichiometric osmium because it's very expensive and it's quite toxic. So what's the mechanism? You have concerted formation of the osmate ester followed by hydrolysis to free the diol. So in this case, we form two carbon-oxygen bonds via formation of the osmate ester, and the osmate ester is then hydrolyzed to yield the syn 1,2 diol. Once again, dihydroxylation is stereospecific. So if you start with a Z-alkene, you get a defined product stereochemistry. If you have an E-alkene, you get a diastereomeric but defined product stereochemistry. With that in mind, I'd like you to predict the product of the following reaction and draw a mechanism for this reaction. You do not have to show the mechanism for the hydrolysis step. I just want to see formation of the osmate ester and the final product. So pause the video, work through this example, and then we'll discuss momentarily. Okay, so in this case, we have a defined E-alkene. The first step in this reaction is formation of the osmate ester. From here, that in turn installs the osmate ester with both of the oxygen atoms on the same face. After reduction and treatment with sodium hydrogen sulfite, that in turn yields our syn diol. And in this case, we do observe this product plus the enantiomer. Wonderful. Now, what can we do with diols? Well, diols can actually be subjected to a reaction known as oxidative cleavage. So we can treat vicinal diols, which are 1,2 diols. If you have an alcohol at carbon 1 and 2 at adjacent carbons, these are known as vicinal diols. Treatment of vicinal diols with, in this case, the periodate anion breaks the carbon-carbon bond to yield a ketone and aldehyde product, depending on substitution. So we can take any diol and convert it to a pair of ketone and aldehyde products. Net, we break this carbon-carbon bond and we oxidize both of the alcohols to the corresponding carbonyl. So what's the mechanism? First, you generate what's known as a periodate ester via attack and attack. Once you have this periodate ester, it undergoes a concerted bond cleavage to break this carbon-carbon bond and generate two carbonyls. As you can see, if the alcohol is highly substituted, you get a ketone. If the alcohol is not highly substituted, you get an aldehyde. So let's try to apply what we've learned and let's predict the product formed from the following reaction. So in this case, in our first step in dihydroxylation, we would generate the syn 1,2-diol. After step 2, we would break this bond and we would end up with a mixture of aldehyde products. Let's now think a little bit about how we can think backwards, knowing how a reaction behaves. And let's think about what starting materials would we need to yield the indicating product for the following reaction. So what alkene starting material can we use to make these two products? Let's pause the video. I'd like you to take a few moments to think and work through this problem, and then we'll discuss. Okay, so first and foremost, because we're looking at oxidative cleavage conditions, let's think about what happens if we were to connect these two carbonyl carbons. So on the left, we have two methyl groups attached, and on the right, we have one methyl group. So if we use this starting material under these conditions, we would first get the diol, and then from there, oxidative cleavage would give the ketone and aldehyde product respectively. This type of thinking is going to be used a lot in later chapters, and it's an introduction to what is called retrosynthetic thinking. Now, in addition to oxidative cleavage, one other method to cleave carbon-carbon double bonds is ozonolysis. So treatment of an alkene with ozone yields a molozonide, which converts to an ozonide under the reaction conditions. Now, if you employ a reductive workup, such as zinc or dimethyl sulfide, you yield aldehydes, while an oxidative workup with hydrogen peroxide yields a carboxylic acid. Net, we break this carbon-carbon bond and either generate a ketone and aldehyde or a ketone and carboxylic acid. Key thing to remember, if we use a reductive workup, we get aldehydes. So reductive workups yield aldehydes, while oxidative workups yield carboxylic acids. Note, you have to work up the ozonide. These intermediates cannot be isolated safely in that they're highly explosive in many cases. So before you finish the reaction, you usually work it up with either an oxidizing or reducing agent so you get isolable products that are not explosive. So what's the mechanism? In the first case, you end up with cycloaddition of ozone. So ozone, which is O3, reacts with your alkene. You get a molozonide. That molozonide then rearranges. First, we break bonds and generate these fragments. And then those fragments then recombine One moment. Those fragments then recombine and recyclize to generate the ozonide. So in this case, now that we've discussed the mechanism for ozonolysis, and we'll talk about the reductive and oxidative workup, I'd like you just initially to predict the product of the following reaction, and I'd like you to tell me if I take this alkene and treat it with ozone and dimethyl sulfide, what product would I get out? So pause the video, work through this example, and then we'll discuss. Okay, so first and foremost, dimethyl sulfide, this is reductive. So we're under reducing conditions. So we'd expect to observe aldehydes and ketones. So in ozonolysis, for predicting the product, you just break that carbon-carbon double bond and you draw out a carbonyl at each of the carbons. So in this case, we get cyclopentanone and this short chain aldehyde. Key thing, reductive conditions, you observe an aldehyde. Okay, let's talk in more detail about reductive versus oxidative workups for ozonolysis. So reductive workup of the ozonide yields aldehydes and ketones. Common reductive workups involve adding zinc or dimethyl sulfide or triphenylphosphine. So under the reductive workup conditions, for example, with dimethyl sulfide, you end up with attack and reduction of the ozonide, followed by elimination of your leaving group. The main driving factor and one of the main driving forces is the fact that you're generating this highly stable sulfur-oxygen bond. So the reason why triphenylphosphine and dimethyl sulfide can work as efficient reducing reagents is that they're reasonably nucleophilic and they can be readily oxidized. So as you can see, after elimination, you end up with not just one aldehyde, but two aldehydes. If your substitution, if you have a more highly substituted ozonolide, you'll observe ketones and aldehydes instead of just aldehydes. The oxidative workup is a little bit interesting. Oxidative workup of the ozonide with hydrogen peroxide yields carboxylic acids and ketones. I'm going to be upfront that the mechanism for oxidative workup is quite lengthy, and you're not going to be responsible for the oxidative workup mechanism. The key thing I want you to note is oxidative workup of the ozonide yields a carboxylic acid instead of an aldehyde. So with that established, I'd like you to predict the products from the following reaction. So pause the video, take a few moments, and then we'll discuss. Okay, so as always, for ozonolysis, you break your carbon-carbon bond and we generate two carbonyls. In this case, because we're under oxidative workup conditions, 1, 2, 3, 4, 5, 1, 2, 3, 4, 4, 5. Instead of getting an aldehyde, because we're under oxidative workup conditions with the hydrogen peroxide, we get a carboxylic acid instead. So here's the product that we have observed from this reaction. So ozonolysis is really useful to break carbon-carbon double bonds and generate the corresponding carbonyl compounds. Let's conclude this chapter now by discussing radical hydrobromation and radical additions. So treatment of an alkene with HBr and peroxide, be it tert-butyl hydrogen peroxide or hydrogen peroxide, treatment of an alkene with HBr, a peroxide, in the presence of heat yields radical addition products. Radical addition occurs with anti-Markovnikov regiochemistry, where the bromine atom is installed at the least substituted position, and you get a mixture of stereoisomers. The mechanism is unique compared to traditional polar hydrobromination in that the addition occurs to generate the most stable and most substituted radical. The radical then abstracts a hydrogen to place the hydrogen at the most substituted carbon. The full mechanism involves initiation, where the oxygen-oxygen bond breaks. You generate this oxygen-centered radical. It then propagates via abstraction of a hydrogen from HBr. You now have this bromine radical, which then adds to your alkene. Notice here that we are adding to the least substituted position. The reason for that is we get the most substituted radical. The radical that's generated then abstracts a hydrogen, and this yields our hydrobromination product. Notice it is anti-Markovnikov regiochemistry. So let's apply what we've learned and let's try to predict the product from the following reaction and draw a mechanism for this reaction. So pause the video, take a few moments, and then we'll discuss. Okay, so first and foremost, in radical hydrobromination, we first have to initiate this reaction. So we have our peroxide. We're going to break that oxygen-oxygen bond and generate this oxygen-centered radical. From here, we're going to pull off a hydrogen via abstraction. That generates an alcohol as well as the bromine radical. From here, we can use that bromine radical. The bromine radical is going to add to the least substituted position, and addition is going to occur to yield the most substituted radical. From here, our product will abstract a hydrogen to continue on the radical chain, and this yields our hydrobromination product. As you can see, bromine was installed at the least substituted position, which is unique compared to acidic hydrobromination of alkenes. So with that, we've discussed all of the major mechanisms for alkene addition, and we've practiced in multiple cases predicting the product for alkene addition reactions. This concludes our Chapter 7 lecture, and we'll be continuing on with this lecture series, moving on to Chapter 8, focusing on the reactions and chemistry of alkynes.